Okay, I'm going to move around the camera a bit and talk to you about the setup. This time between L and M is scaled. This is really scaled out to the transfer beam here with the that they use to hold the planter box and the elevation change. The elevation change seems to work out at the 11 inch. Remember, there's 11 inch elevation. Let's establish some rules here, and let me see if I can talk louder for you guys. So let's establish some rules. This is our elevation of our deck. Whatever you want to call it, maybe add more finish on it, still elevation change is the same. An 11 inch elevation change. Top of deck, so you get to the top of the deck of the entrance or the coming out of 111. That appears to be the 1'6" also. When I did relooked at this, revisited, and I came down to here, and I did the 11 inch. Tape measure is real handy, not? Okay, so I did the 11 inches back here. So there's your 11 inches. There's your 11 inches. Okay, so if we count the 11 inches, and I think about the lobby, right? So the lobby's about 8 inches thick or so, plus or minus. But let's say that top piece of steel is the lobby. Looks like I've got a focusing issue. There we go. So let's say the top piece of steel is the lobby, and they have a 7-inch deck elevation change, so you step down 7 inches. And if I add the 7-inch step down and the 11 inches that it would be stepping down onto, I come up with 11 inches plus 7 inches. Well, that's the 1'6". So that still comes out to 1'6" in front of this area here. Now this column doesn't exist. This is just so I can leave this in a position where you can start visualizing better. That does not exist. Imagine it being flat and plain straight across. So this would be straight across, and this would be straight across, the one in front. Noteworthy is this is M, I'm looking at my notes, extends out to this location. This location from the face of the wall out is 10 foot, correction, 19 foot 10 inches to the 19 foot 10. When I do it from L, the plans say it is 19 foot 4 inches. So that's that would be the gas can. All right, there's the gas can. So there's a 6-inch offset in the length of this transfer beam. 6-inch offset, so they're not parallel with each other. Now with that said, I want you to look at that. Imagine a butterfly coming over to this span, and now look at how it reacts. And one of the reactions that might happen to get your planter box kind of flat over there. So this is not, the planter box is further down, but I took a little liberty and just shoved it over here for now. That's that piece of steel. It says planter box. It's not true. It's further down. It's between that piece of steel, which is not scaled yet, and to that piece of steel. So imagine as it's breaking, that if this wanted to shear apart, it might be, so it's as close to a column. That is L. See the L on it? Since that's close to a column, this might want to break similar to what we see here. It might want to break with a little bit of a cantilever and come down. And on this side, I just had it pivot from there. I'm going to show you what I show a lot of demolition guys on different job sites about the pry bar or the lever effect, cantilever, however you like to see it. You know, you give somebody the longest bar, and they can lift up the world, supposedly. Well, imagine the prying effect once this goes down, how it wants to shear and separate from this side of the structure. If this section is going down, you can see it there. Oh, sorry. You can see it here. So if we put a this would be the top of the new deck though. So then it's a faced wall down to here. So this one will pry away for free, but in the building, at the building side, I have to see if you should see in the camera. On the building side, we might get a different look altogether. And let's see if I can do this. Good. On the building side, that would have an effect of pushing up on M or prying M apart instead of just pulling away for free as some modeled, computer modeled is doing, is just pulling away for free without having any prying effect. Let's show you the prying effect. Oh, this is heavy. Hold on. Hold on. It's not a light one. Not a light one. Yeah. Oh boy. So now, hopefully you can see it. Let me see if I can wave and see myself. I'm not sure if you can. But as this goes down, this has a prying effect of pulling at this column. As this part of the structure goes down. Okay. Hopefully, let's see if you could see that. Yeah, you could have. Okay. So you can imagine if that's on top there, the prying effect of ripping it apart, not pulling away, as some of these computer models show, or these fake computer models, or you know, let's face it, like Mike Bell's video, having it just pulling away for free. No, it also has that prying up effect and ripping out effect of creating a void in there. It's not just pulling away like somebody could keep it still and then magically just pull it forward. No, it's going down, and when it goes down like that, it has the pry effect there, and this one, it can just break away for free because it's elevated out here, not integral with the building at that point. But depending as it drapes, it's going to want to pry away and maybe pull away too. So on like a 45, depending on how this break is here. Now, as you can see again, you get the prying out here, looking like that, similar to that, going down. That's with that cross BMA failure with the planter, with the elevated deck. The planter box was over here on the other one. This is the elevated deck, and of course, if I raise it up, it would be 11 inches. If I raise that up, it would be 11 inches. So now we have. Now you can see that now there are hooks that go into each one of these. Hooks go into, I'm going to talk louder again. So the deck is, on this side is hooked here. So this wants to pretty much just make that hook fail, because right out here, right out there, is where we had the inspection hole. Not back here. Alright, so we can get it failing there. That can create that effect here, which would also can have effect of a little bit of prying action, falling down and pulling this over. Of course, it's tied to the structure with hooks again. So it's tied to the structure with hooks. Those hooks want to start pulling this down. That leaves it at 1'6", not as stable as it can be. And when it goes down, about 7 minutes later or so, it has a prying effect on the columns, the two outside, the M and I think M is our line, right? M is our line if we look at the roof line. If you look at the roof line, M is where the building, isn't it M where we found the, where we watch it shear down? It's in line with M, shear away, so M is one of our shear planes, one of our stopping points, as it takes down this slab, goes down and starts pulling that slab to the left. So I believe our slab failure is first between L and M. And as L and M goes down, let's do that now. I'll show you what that would look like. I have to talk louder. So as L goes down, it's connected over there. It's a long slab. It's no longer there, but it could go down like this, where it pulls away that, rattles it a bit, stays stable. But remember, when this goes down, it's still connected to the backside inside the internal floor slabs. It's connected there. So that has some weakening effect. So if this goes down there, if it loses it there, and this hits the floor, that would be standing by itself until it reaches around and grabs it. But right now, it would look more like this. This is the drop slab detail I was trying to show you. But, so then, that would go down like that. And when it goes down like that, as it if it could, which it cannot without lowering first, the middle section has to fail first. This doesn't just shear off and drop free. There's no force to do that there as far as I can gather. So now everyone is claiming that this is our magical mystery missing column, that it just buckled. We have no evidence of that, and we just had some crazy extrapolations just because you can't see it in an image. But we have data that shows that no column buckled in all of them. None of them buckled, but it happens to be the one in the image that they take. The only column that can't be accounted for in that, well, you can't account for anything in L either, but the one that they give because they can't see it, they decide it doesn't exist. Well, there are other columns behind it. You can't see those either, but yet we can see them when we look at the day images. We see it poking up. Oh, so we just say that counts, and this one just decided to buckle on its own and disappear. Nevertheless, even if it did buckle on its own, it's not the beginning of the failure. Unless, of course, somebody rammed it with a car. We got nothing of a car being left there, you know, and the car wouldn't, yeah, you'd have to be pretty damn, no, I'm not there. And remember, we have a truck that was supposed to have come in and they saw water, and then they turned around and left. They hit the gates or something, so there's power there at one point. Or they came up to the gates and they saw the water, turned around and left. So that's a bit of a timeline addition also. But I think it's a truck. The person, I recall it was a truck. So I just wanted to get this up to you and give you an idea, more of an idea of how you can start visualizing how this patio outside 111 could present, and also how if this fails in the middle, as it butterflies through, how it would also do some damage to the column on M, the face of it. Of course, we have a shear point at that point, and what I mean by shear point is that we have the video doesn't appear, I'm taking liberty here, doesn't appear to go past the, let's see if I get this right, the face of the building. And that's where our links, where our 90s are. Our pad is separate from our building, our 1.6 elevation, our drop. I call it a drop slab, and I keep doing that. It's a slab drop. There is a difference. So drop slabs are the repairs, right? They're slab drops. So the slab drop is 1.6. So please forgive me in all the videos where I keep inverting that sometimes. So we get our failure. So we get our failure butterflying through, more than likely ripping away from there, butterflying, and causing a rattling of the building as it breaks free. Not the vibration on hitting the ground and vibrating through the building, but it now rattling M and L, and by rattling L, we then get the lady up there in 611, she's a crack in a wall, and jets. We get Cassondra, Billedeau, Stratton, Cassondra, not A, sorry, I apologize for that. Cassondra, Billedeau, Stratton, making a phone call to her husband, which we hope will lobby and make up a Cassondra Stratton, Billedeau Stratton law that would help with any renters, that they must disclose the structural repairs that are coming or they know of at the time, and allow the people to exit the contract. And also they should consider all elevated parking garages, which includes the parking spaces, what I'm driving at. Anything you drive over that's elevated as a bridge, period. Just consider it a bridge, and that requires a 2-year inspection. Bridges do. So, you know, yes, it's on private property, and private property doesn't require bridge inspections, but that's not true also, because a lot of bridges are privately owned. So, you know, that's weird, and it's publicly used. So, you know, I'm giving a take with that statement. So there is precedence to say that you can demand that the 2-year extend to these structures and call them bridges. Call them bridges, especially because they're connected to the main structure. So it also caused that. So then we have an expansion issues. We have no expansion and contraction connections. We have no to the whole building. Yet we have heat, multiple ranges of heat, if you will, across this entire structure. We've got the sun that can hit by the pool deck, which is cooler, or hotter rather, and cooler around the pool, and then cooler underneath of the overhangs. So you got this gradient that's going on there too, that's going to give you your expansion and contraction issue differences. You got your cool building meeting your heated surface over here, which helps with the problems. You've got the watered surface with the down here would be the planter boxes, where you're cooling that area off. It's covered, in fact, and so that creates gradients and all types of interesting dynamics with expansion and contraction. And it's concrete. You know, it's doesn't like not being able to move when it's expansion and contraction. And here we go. That's about the size of it. Wait a minute, let's do this over there. So I took a little liberty there, and I added this extra piece of steel on the face of that. See how the larger piece by the level? That's sort of to help you identify that the column, the beam, has different sizes on it. It looks like this cross member beam, this one, is tied into it at some point. So it's as if it was pretty interesting how they must have formed it. I can't tell. I can only theorize that the cross beams were formed, and everything was formed to be integral to interlock. But they also have, at this point right here where I have this beam, I'm sorry, my fingers aren't showing yet, right where I have this beam, again, more shear links. This is like individual, shear links. There's more hooks that puts this pad up here as a separate pad. It's an elevated separate pad supported by, on the outside here, by this beam here, the elevation of 11 inches, and on the wall into the 1'6" slab drop, not drop slab, slab drop. It's supported into that structure. Of course, that is integral over to M, tied in there. So when it goes, it yanks on it, especially if we can get this cross member to come down. It really will do prying. Now let me show you a better angle of that. Let me walk it. Let me walk and keep it live. Turn it around so you can get a better angle of what I'm talking about here. Let me do this. So now I'm going to show you if we can get remember that that thing out there is where the column is, the column is, and this is it would be a continuous beam out to here, concrete, reinforced. This is scaled. That's 11 feet. All right, so now as we get that, if we can get that to drop down, this beam here to drop down, we'll then also get a prying action down here, which would also be integral to tearing up this corner. So what I'm going to do is I'm going to try to do two of them at the same time. So I might move the steel, I might not. Let's see. So if you watch down there with the bricks. If this could drop down, watch your bricks here, and you can watch. You can watch both if you like. Well, I just lost my centerpiece, but you see the way now it's no longer there. And as this goes down even further, it has a ripping effect away from the column even more. It has a ripping effect of that away from that column even more so. And that would be there. I'm going to, sorry about the background noise, meaning the other things in the images. Let's see if I can move one of them for you. I want you to be able to see one in the background there, so you can see the difference. So you can see the change. Okay, good. So you have something to reference. All right, good. I'm going to lift that back up over here, and then I'm going to lower it, raise and lower, and you can see the effect it could have on a column there. So, just wanted to cycle that a few times. We're not done with this model. This is just another step for you to start visualizing and seeing what's going on. All right, doing that, we get that separated. We get this slab dropping internally here. That slab dropping internally would be our column, what is referenced as a column failure. Could be this M. And then it's being redundant with across the structure, and our shaking's got to come out to here too. We're going to shake out to K and L, because we're going to lose the top two floors, and I think that's because we're looking at the reinforcement. Let's come over here now. The reinforcement is only times at the top is only times 4 pieces, not 6 or 8 or 10. So we're going to take a look at this real quickly. I'm going to remove, oh wait, let's turn it on an angle here. So you can see the redundancy was 6, well not quite redundant because it's a different moment for each one, but you can see that if I remove 2 of these, now we're down to that column at the top of the roof, meaning up at the top floor. There's only 4. I want to make sure this thing's not moving anymore. Good. There's only 4 pieces of rebar up there. If it rattles or if it shakes and you lose 1, you're down to 3 now. Now it's trying to get stability, but it's got no spine. Doesn't have the ability to grab, and you've weakened your connection with your deck. Your deck now wants to also pull away from here. That puts it out here. Your spine is now lost. Your tension going this way, you just lost it. So if you lose 1 of them even, so if 1 of them was to fail, now you've got this, now you're down to 3. And it's trying to hold it here. That buys you some time. That buys some time while the deck has what I call accelerated creep. Remember, going back to the garage video in Texas, how you saw 7 minutes went by. It looked stable. It appeared stable. Firemen were underneath of there. And approximately, just like this one, 7 minutes went by, and if those firemen were there, they would have been plowed over by that beam, the beam for the deck. But just by chance, they weren't there 7 minutes later. Just by chance. But there was no way they were getting out of the way if that thing rolled, if they were there, because they were right underneath them. All right. That's just, all right, so let's see. Again, so the building tried to settle down. It settled down. Phone calls were made. end the video. We'll get more of this content going, and these models aren't done. I'm going to show you some pull-out rebar test, things like that. But I'm going to wait till actually have a date for that. January 8th, I think it is. I'm letting some maturity happen with something else I'm experimenting with. Okay. Oh, let's end it with that. If that goes down, and incidentally, it's not going down here, or is it? You know, when this goes over, could this have pulled when it came through? Could this have pulled down and then pulled this one through? Because remember, our span is from there to here, and our supporting is more critical shear area and tributary area around it, so steel around it. And on this one, on this side, it's only in the hooks, only in the depth of that slab drop detail. It's only a little bit, so it has a very high chance of pulling away from there. And pulling away from there, dropping in this middle, sagging in this middle, so I'm trying to do a two ways direction here. So sagging this middle, pulling that off, rotating off of the deck here, the top of the deck, falling down. Remember, it's an elevated slab, so it can go down separately, and it can actually leave this deck pretty much intact. You know, they don't really talk about it as a drop slab detail, and it doesn't look that way. It looks like an integral beam going across with this over here also. When I say integral, I mean, yeah. Now I'm going to stick it with that because it's not quite, the beam system, the BMA system appears to be one system with the rebar hooks on it, ready for the slab to drop the slab elevation change into it. Hopefully I'll refine this and hopefully you understand it more, but maybe this visual from here will help you see. Oh, and again, this is scaled. That's 22 feet. Looking at my notes. There's the tape measure in the background there. That's 22 feet 6 inches, and between L and M, and between K and L is 21 feet 6 inches. All right, the width wise. Take care, guys. Bye. And ladies.